Welcome. Today we're going to talk about how to draw a free body diagram. First of all, you need to understand what a free body diagram is. A free body diagram is just a dot. The dot is surrounded by forces that are acting on the dot, such as the force of weight, a normal force, an applied force, a tension force, a friction force, a buoyant force, another tension force, and so on. So there are lots of kinds of forces that can be acting on this dot. But we don't need to really worry about that when we're trying to draw it. What we need to do is just follow a few simple rules. The first rule is there gravity acting on the dot? And if there is, we're going to have the force of weight. Sometimes weight is written as an F with a small mg to indicate that the force of weight is due to mass times gravity, which is 9.8 meters per second squared. But we're going to probably stick with Fw in this class. The next thing you want to know is it sitting on a surface? An object sitting on a surface is going to have a normal force. That means it's perpendicular to the surface that's going to be pushing on the object. Is there something pushing or pulling on it? So these can be labeled many different ways. F sub A could be the applied force, Ft could be tension, Fb could be buoyancy. There are many ways to label forces, and they should kind of become intuitively obvious once you read the question and look and see what kind of forces should be acting on the object. Is there friction? Generally, it's written as F sub F for the force of friction, and that's generic friction. You may also see F sub S for static friction, or F sub K for kinetic friction if the object is moving. Is there acceleration? And this is the last point, and there's no F for acceleration. The acceleration F is the net force. It's the difference from all the other forces, or if you sum them all up, left with something left over, that net force is what causes acceleration. Also, the arrow's length represents the magnitude, so a longer arrow means a stronger force. Let's use these rules to figure out how to draw a free body diagram for this example. A car driving at constant speed to the right. So the first thing we do is we start with our dot. And we don't need to worry about driving at constant speed to the right now. Let's just go through our list. Number 1 says, is there gravity? So yes, there's a force of weight, sometimes written as Fmg. Is it sitting on a surface? Yes, it's sitting on the road, so we have a normal force. Is there something pushing or pulling it? Well, the engine is applying a force to the tires, which is applying a force to the road. So yes, we have an applied force. And what about friction? Yes, we do have friction. If we didn't have friction on the road, the car wouldn't move. The tires would just spin, so there is friction. Last one says, is there acceleration? Well, it says it's moving at constant speed. So constant speed means there is no acceleration. That means it's at equilibrium. So equilibrium could be not moving at all, or it could be moving at constant speed. And what that means is the net force must be equal to 0. In this example, a light bulb is hanging freely from the ceiling. So what do we know about this? Is there gravity? Usually is, so we have a force of weight. Is the light bulb sitting on a surface? No, it's not. It's hanging, so there is no normal force. Is something pushing or pulling it? Well, yes. If it's hanging by a cord, then there's going to be a tension force above it. Is there friction? Well, it's not sitting anywhere, it's not, and friction would have to be resisting some kind of force anyway. So since it's not moving or being pushed on, there's no friction force. And is there acceleration? Well, the light bulb says it's just hanging there. It doesn't say it's falling or doing anything else, so we're going to assume that there's no acceleration. Again, at equilibrium, which means something is not moving or moving at constant speed, the net force must be equal to 0. So these two lines should have exactly the same magnitude. One is up and one is down, and they should cancel each other out and equal 0. How about this example? A freely falling rock speeding up as it falls. The first question, is there gravity? Yes, there is, so we have the force of weight. Is the rock sitting on a surface? No, so there's no normal force. Is something pushing or pulling it? The answer to that is also no, and not unless it was hanging by a string or being pulled over the edge of a cliff or something. Number 4 says, what is there friction? So what about that? When something falls, generally it's resisted by the air, so there is some air resistance or friction from the air. So let's go on and put in a friction force there. And what about acceleration? Well, we can look at the problem statement and we see that there are some key words here. Free fall, freely falling. So it's in free fall, so that tells us there should be some acceleration. It also mentions that it's speeding up as it falls. So is this at equilibrium? The answer is no, it's not. It's speeding up. When something is speeding up or changing its velocity, F net cannot be equal to 0, which means one of these lines cannot cancel the other line. So we're going to shorten our friction and leave the force of weight the way it is. So the friction is not completely canceling the force of weight, leaves it with a net force pointing down, which is why it's speeding up as it falls. What if this rock was on the moon? In that case, there wouldn't be any air, so there'd be no friction, and we would just have it falling at whatever the acceleration due to gravity is on the moon. How about this example? A car speeding up to the left. So the first thing we need to do is see, is there gravity? Yes, there is. Is it sitting on a surface? Yes, it's on the road, so we have a normal force. It's not flying off the road or going down into the ground, so they must be equal to each other. Is something pushing or pulling on it? Well, it's got an engine, so it has an applied force going in one direction. And is there friction? Yes, there must be, because otherwise it would be standing still as the wheels spun. So there's a friction force. The last one says, is there acceleration? Well, the car says that it is speeding up, so there must be acceleration. Is this at equilibrium? No, not if it's speeding up. That means the net force cannot be 0. So one of these arrows, the left or right, must be greater than the other one. Since friction can never be greater than the applied force, we'll just shorten this friction arrow, and the net force is pointing to the left, which is the direction the car is going. Wherever the net force is pointed, that's also the direction of the acceleration. Lastly, let's look at a weight hanging by 2 wires. We start with our weight, and yes, there is gravity, so there's an arrow pointing down. Number 2, is it sitting on a surface? And the answer is no, it's not. So no normal force. How about something pushing or pulling on it? Well, it did say there were 2 wires, so we have a tension force from wire 1 and a tension force from wire 2. Is there acceleration? Oh, is there friction? Forgot about that. It's just hanging, so we're going to assume no friction. Is there acceleration? It just says it's hanging, so again, not moving. That would mean that this was at equilibrium. At equilibrium, the net force must be equal to 0. Well, we've got some odd angles here that we haven't seen yet. So what can we just qualitatively understand from these 2 angles? The first is that the left and right have to cancel each other. If they didn't, this would be moving to the left or right. So the left part of T1 and the right part of T2 must cancel out. What else do we know? Well, we know that the vertical component from T1 and T2 must cancel out the force of the weight. So they're shorter arrows, but combined the vertical part of each one of those added together must equal the vertical part of the weight going down.